to function sharing by meromorphic functions and factorization of meromorphic functions, normal families, and dynamics of meromorphic functions. Presently, he is an office bearer of Ramanujan Mathematical Society. The title of his talk is The Normal Families of Holomorphic Functions of Several Complex Variables. So with this brief introduction, I invite Professor K.S. Charak to start his talk. Sir, please.
Yeah, thank you, Professor Sanjeev. Nice to see you again. And am I audible?
Yeah. Audible.
Sir, yes, sir.
I'm thankful to IMS for giving me an opportunity to present my talk here. So the title of my talk is going to be Normal Families of Holomorphic Functions of Several Complex Variables. So I will be starting with this basic stuff first, because I will be discussing results in one variable theory first, and then I will go to the several complex variable setting as promised. So by C we shall be by D we shall be denoting a domain in complex plane, and we shall be concerned with the meromorphic functions f from D to C bar, where this is going to be Euclidean metric and C bar is equipped with the caudal metric, which is equivalent to the spherical metric, as we know. I will be using the notations HD, set of all holomorphic functions on domain D, MD, the set of all meromorphic functions on domain D. And by normal convergence, we shall mean that the sequence in HD or MD, it converges uniformly on compact subsets of D in the Euclidean or the spherical metric, depending whether we are in HD or MD. So there is on the function spaces, this HD or MD, we have to make them the metric spaces first. And for that purpose, we have this metric of uniform convergence. It is introduced as follows. We take the compact exhaustion of the domain D, by a sequence of compact subsets of D, we satisfy these conditions. And for all f in HD, set of holomorphic, that means for every holomorphic function on D, we define this norm of f to be the maximum over Kn mod Fz, and this maximum will always exist because Kn is compact and f is holomorphic and so continuous. Then we define this function D from HD cross to HD. That means this is a distance function, so we give it by this, and this comes out to be a metric on HD. And see, this is the this Euclidean metric. Here, if this Euclidean metric is replaced by your spherical metric, and we take the class MD in place of HD, then we get the corresponding spherical uniform metric on MD. So this HD and MD, these are going to be the metric spaces under the metric of uniform convergence defined like this. So actually, what we are interested, we are basically talking about the compactness of the metric spaces. Particularly here in normal families, we shall be talking about pre-compact or relatively compactness of the HD and MD. And this is very important and concept in topology and analysis, because we say that XD is a compact if and only if every sequence in X contains a subsequence which converges to a point of X. These HD and MD are metric spaces. So to extract a subsequence, convergent subsequence from a given sequence in these spaces, HD or MD, it is of great interest and importance in complex analysis. And this gives rise to the notion of normality. So precisely how normality is defined, you take any subfamily of your MD, this is the family of meromorphic function on domain D. We say that it is normal on the domain D if every sequence of F contains a subsequence that converges normally with respect to the spherical metric to a limit function, which is meromorphic, or it can be the constant infinity. Normally means it converges uniformly with respect to the uniformly on compact subsets with respect to this spherical metric. And for a normality at a point, we need to have a normality in a small neighborhood of that point. And this is basically a local property. And you know that by Weierstrass theorem, if we take this family, we take this f to be a subfamily of hd, then the limit functions that we talked about here are holomorphic or can be constant infinity as well. So anyway, the first important result in this direction was given by Arzela-Ascoli and by two Italian mathematicians in 1890s. And the result precisely says that if you have a subfamily of continuous functions from a metric space X to a complete metric space Y, then F is normal. If and only if F is equicontinuous on compact subsets of X, and for every X in X, the closure is going to be compact. So this is basically Arzela-Ascoli theorem, and it gives us the equivalence between the notions of equicontinuity and normality. So these are equivalent notions by this Arzela-Ascoli theorem. So basically, the normal families were introduced in 1907 by a French mathematician, Paul Montel, in his doctoral thesis submitted to the University of Paris. And about this theory, one of the great mathematicians, namely a French mathematician, namely Henri Malus, in 1947, he said the following about these normal families, how important these families are going to be. He said, I quote, the theory of normal families of functions should be regarded as one of the most beautiful discoveries, and most importantly, its fruitfulness in the first half of the 20th century. And it has enormous amount of applications. To mention a few, theory of functions in one and several complex variables, holomorphic and meromorphic dynamics, the dynamics of Riemann surfaces, the theory of boundary sets, function analysis, and many others. So basically, the one of the fundamental results, the normality criterion that was proved by Paul Montel, that is as a consequence of Arzela-Ascoli theorem. This is known as what you call Montel's theorem. In literature, we call it as Montel's theorem. You take any subfamily of your HD, that means you take a family of holomorphic functions on a domain D. It is normal if and only if it is uniformly bounded on compact subsets of D. So this is the most fundamental result. And the immediate application of this result, we have the Riemann mapping theorem. We can prove the Riemann mapping theorem by using this Montel theorem on normalities. And then there is another criterion for these holomorphic functions, normality criterion. If each member of this family F omits two fixed values, complex values, then that family happens to be normal. That means if you consider the family of holomorphic functions from a domain D onto two punctured plane at two places, so then such functions constitute a normal family. And this has its extension to meromorphic functions, I will mention later. But before that, we have another notion of derivative, that is spherical derivative, because once we have the spherical metric, then we have the corresponding notion of spherical derivative for meromorphic functions. And that is given by this expression basically. When z0 is not a pole of the function, and if z0 is a pole of the function, then we simply take the limit of this expression. So, and this spherical derivative is a continuous function, and if f is not identically equal to 0, then the function f and its reciprocal have the same spherical derivatives. And this is most important thing, most important. This thing does not hold in ordinary derivatives. This thing happens only for spherical derivatives. So there is, as we talked about the Montel's theorem, it says that it is normal if and only if it is uniformly bounded on compact subsets. But here we have a corresponding result where the spherical derivatives are going to be uniformly bounded on compact subsets. That is known as the Morty's theorem. This is another important criterion which is most useful in the theory of normal families or of meromorphic functions. See, this is a family of meromorphic functions is normal on a domain D. If and only for each compact subset K of D, you can find out a positive constant depending on K, such that the spherical derivatives are be uniformly bounded spherical derivative of each f in F. That means every member of F has a uniformly bounded spherical derivative. This is Morty's theorem, and this is most useful. And as a consequence of this, we can prove that this normality is going to be a local property. And for that sake, we just always consider our domains, or we discuss the normality on the unit disk being a local property. Yeah, there is because this Morty's theorem cannot say anything about functions which satisfy this kind of property. And this situation was dealt with by Royden, and he proved that F is going to be a normal family if it has the following properties. That means for each compact subset K of D, there is a monotone increasing function Gk. Remember, this depends on K, compact set, such that derivative is bounded by this function here on the compact set K. So this is Royden's theorem. This Royden's theorem was further sharpened by Schwick, and he proved that we do not need the monotone function as Royden did. Basically, we need a function hk which is finite somewhere on this. That means even if we get a single point of this interval where this function happens to be finite or takes a finite value and satisfy this condition, then this is going to be normal. Yeah. And see, the proof is very, very beautiful, because I can show you this one. Because if you take a compact set K in D, you fix it, and you take any point y naught greater than 0, that means y naught is a point in the interval 0 infinity, such that at which the function has a finite value. Because we are saying that if we have a function hk which is finite somewhere in this, suppose that is the point y naught where the value is finite. Let us take mk to be the value of hk at y naught, because this is finite, so we can consider mk to be this. Let us define ek to be the circle with center 0 and radius y naught. Then see, the spherical derivative is always by definition less than equal to the derivative of the function, modulus of the derivative of the function, which is by our hypothesis less than equal to this. But remember that this thing is going to be hk of this thing is going to be hk y naught, because this thing will happen only on this set ek. Because this on this we have this y naught, so that means mod fz will be equal to y naught here. So this is mk whenever z is in k and fz belongs to ek. So for every fz in ek, that means image of z in ek, this inequality is satisfied. But remember that this is Morty's condition. That means the spherical derivative is uniformly bounded on compact set K, therefore it has to be normal. So this is most simplest, shortest, and meaningful proof of this extension of Royden's theorem by Schwick. And if you look at this, that means this Ek, it is just, we are talking about things on a circle. We need a circle. But this can further be refined, as there is another result that is proved by Wang, published in the lecture notes, published in Decker, New York in 2000, by using Zolzman's lemma. Anyway, I will go to that later. What is that Wang's theorem? See what he says. Let there be a family of meromorphic functions on a domain D in C with the property that for each compact set K, there is a function hk into this interval on extended complex plane, which is finite for at least 5 points on C bar. If we have this function which is finite at 5 points here in the extended complex plane, and satisfying this condition, and this condition is satisfied, then definitely this family is going to be a normal family. Remember now, the set where this function is going to be finite just at 5 points, then this happens to be a normal. Instead of a circle, we just take this to be the set of 5 points. But for holomorphic functions, we need only the set consisting of at least 3 points. If we have a set consisting of 3 points in C, at which this hk, the function hk here, is going to be finite, then the family happens to be normal. So this is an improvement, I should say sufficient improvement over Schwick's theorem. And there is another thing, heuristic principle, I should say, heuristic theorem. We call it as Zalcman lemma. It was proved by Lawrence Zalcman in 1976, published in American Mathematical Monthly. And this is a small theorem, but it has abundance of applications, which I can say that has revolutionized the theory of normal families. This is basically, in short, I would like to say that this Zalcman lemma is nothing but it is a zooming principle. It is a zooming procedure by which we can construct a non-constant meromorphic function. If we take the family of meromorphic functions, then we can construct a non-constant meromorphic function. Or if it happens to be a family of holomorphic functions, then this is going to be a non-constant entire function. But remember that this construction depends on the factor that f is not normal. So this is for non-normal families. For non-normal families, we can always construct a non-constant meromorphic or entire function on whole of C, right? And this was extended by Peng, and this is known as Zalcman-Peng's lemma. This is for meromorphic functions with zeros and poles with prescribed multiplicities. If f is a family of meromorphic functions, alpha is real, lying between minus p and p. Each f in f has zeros of multiplicity greater than or equal to m, poles of multiplicity greater than or equal to p. Then f is not normal in any neighborhood of z0, if and only if the following thing holds. Again, here this is going to be a non-constant meromorphic function, satisfying this condition that the spherical derivative is always bounded by 1, and this extreme value is taken at 0. So this is going to be, and see this normal family theory that is what we are going to discuss depends heavily on the applications of Zalcman lemma or this Zalcman-Peng lemma in more general setting. And if we take in Peng's lemma, if we take alpha equal to 1 here, alpha equal to 0 here, then we get the corresponding Zalcman lemma. Now see, there is another thing, and that will be the point of diversion for us. From here, I will go to several complex variables. There is a normality criterion proved by Peter Lappan in 1994. The reference is here. And see, this is a, you know that in Marty's theorem, we have the boundedness of the spherical derivative on the compact set. The size of the compact set is not known to us. But here what Peter Lappan has done, he has improved this or reduced the size of that set in Marty's theorem drastically, as I can say. And he proved the following. And this is very genuine normality criterion. A family F in MD is normal on D. D is a domain in C. If and only for each compact set K in D, there exists a subset of the extended complex plane depending on this compact set K, containing at least 5 points. Now see, in Marty's theorem, we have simply the compact set. Compact set may be large enough. Size is unknown. But here he precisely says that even if we have the set of 5 points in the extended complex plane, for which this spherical derivative is bounded, whenever the range happens to be in E, the set of 5 points, then the family is going to be normal. See, this is most, you can say, significantly improved version of Marty's theorem by Peter Lappan. And so the present area which I am going to present now it depends on this. This was the point of interest for me. That what is its analog in several complex variables if I consider the functions of several complex variables. So this is the point, please note it. And there are some other criterions which are very important. These are basically further discussions about Lappan's theorem. Instead of 5 points, if we have 4 points, what happens? If we have 3 points, what happens? If we have 2 points, then what happens? So all these things are recently in 2018, 19, last 2 years, these things are settled. And see that fundamental normality test that I was referring to. Montel proved that family of holomorphic functions which omits 2 fixed values is going to be normal. For normal families, if every member of the family omits 3 fixed values in the extended complex plan, then that family is going to be normal. So this is known as the fundamental normality criterion in normal families. These are some of the references in one variable theory. But now I will go to the this promised stuff that's indicated in my title, normal families of several complex variables. Now see, before I start with this, I would like to make it clear that what we are doing here, there are the discussions on normal families. The theory of normal families of several complex variables is there. But the metrics are going to be different. Kobayashi metric is there, Carathiodry metric is there, under which the normal families of holomorphic mappings are even considered. But see what we are doing here, we are interested in taking one variable theory to the several complex variables, or in a sense, we are going to find out the analog of the results of one variable theory to several complex variable theory. But for that purpose, what we need to do, we need to find out the analogs of the basic results. For example, the Zoltzman lemma, Zoltzman-Peng lemma, fundamental normality test, or for that matter, Morty's theorem. So all these things are to be checked, whether these things hold here or not. But remember, so for that, I have to define the most crucial notion, that is the notion of spherical derivative. Yeah, kindly mute your mics, please. So we are going to define this. See what we are going to do. You take C2 function psi on a domain D, and we define the corresponding Hermitian form like this. This is the Hermitian form, or we call it as the Levy form. In the literature, it is known as the Levy form of the function psi. So by using this Levy form, we define the spherical derivative. We define the spherical derivative by this expression. Taking the supremum over mod v equal to 1 by this expression, where Lz psi v is given by this and log of this thing. But remember that we have to see, is it well defined? Yes, this is well defined, because this thing of which we are taking the root, this is going to be non-negative. This thing is non-negative, and the spherical derivative by this given by this expression is going to be a well-defined quantity. And the most interesting thing about this is that when you take n equal to 1, that means if you go back to one variable, then this spherical derivative is nothing but the spherical derivative of the theory of normal families in one complex variable. So this comes out to be a natural generalization of the theory of normal families of in one complex variable to normal families of several complex variables. And if we look at, we just do little computation, this this expression, I mean this expression, just by finding out the value of this Levy form, particularly for this function, we come out with this expression, that This spherical derivative is nothing but supremum of this quantity. What is this D? D is nothing but this is going to be this kind of operator. Del upon del Z1, del upon del Z2, and del Z upon del Zn. So this is this operator. You just apply this operator, take the supremum out. This is n-dimensional vector. So this is V equal to V1, V2, so on, n tuple Vn. And so once the spherical derivative is defined, and this was done, basically the approach that we are following, it was done by Peter Daubush recently in 2019 in a paper published in Complex Variables and Elliptic Equation. This is a small paper, only that spherical derivative is defined and Zalcman lemma is obtained. Implicitly, it is also contained in the discussions by Cow and Lu in 2016, but they have not said that it is a spherical derivative, but it somehow comes in terms of the total derivative and all that. So Daubush also proved this Morty's theorem in CN. Morty's normality criterion in CN. What's that? Under this definition of spherical derivative, the Morty theorem holds in several complex variables. Precisely the same thing. A family F of functions holomorphic on a domain D in Cn is normal on D if and only if for each compact subset K of D there exists a constant Mk such that the spherical derivative is uniformly bounded. Once this thing happens, then the family is going to be normal, and so that means Morty's theorem is extended or generalized to several complex variables also. This was the first fundamental result that we require in order to take further the theory of normal families of holomorphic functions of several complex variables. Another important thing was Zalcman lemma, and this Zalcman lemma also holds in several complex variables. And this is exactly the construction of non-constant entire function of several complex variables with this normalization. Even the fundamental normality test also holds, because once the spherical derivative is in place, then we can utilize the Zalcman lemma, Morty's theorem, because both of these fundamental results are holding in Cn. The corresponding fundamental normality test is FB, family of holomorphic functions on an open set in Cn, each member of which omits two fixed complex values. Remember, if you have two omissions, then the family is going to be normal. So that means we have three important results in place now. One is Morty's theorem, Zalcman lemma, and fundamental normality test. Actually, fundamental normality test has a very interesting proof. But Professor Sanjeev, may I know that how much time is left with me?
More or less completed in nearing 10:35. So you may take 3 to 4 minutes with the permission of the organizers and
yes, sir.
bearers of IMS.
Yes, sir. 3 to 5 minutes is fine, sir.
Okay, fine. So that means I must directly go to my stuff, that result that I am interested in. So this is anyway, I say keep this. This is the thing that we have proved here. This is a result which is obtained in collaboration with my PhD student Rahul Kumar. And what is this result? The Lappan's theorem. That see, in one variable theory, we need at least a set of 5 points for meromorphic functions and 3 points for holomorphic functions on which the spherical derivative is bounded. This was a point that this is uniformly bounded on this. So this thing was not available in several complex variables. Even we discussed with Peter Daubush, and he was also not able to say anything about this, but somehow we got it proved. And this is most important criterion. As I said, this is the drastic improvement of your Morty's theorem, the set of the size of the compact set. So here we can precisely state the Lappan's normality criterion in Cn as a family of holomorphic functions on domain D in Cn is normal if and only if there is a set E containing at least 3 points, such that for each compact subset K in D, there exists a positive constant Mk for which the spherical derivative is bounded. But remember that this set E has the importance that spherical derivative is bounded whenever Fz belongs to E. So we need this information only. Whenever fz belongs to this set of 3 points and the spherical derivatives are uniformly bounded, then the family is going to be normal. I would like to show you a proof of this because that is most important. What we have done here, we have used the idea of totally ramified values. Totally ramified values means a value is said to be totally ramified for a meromorphic function if it has no simple a points. That means f minus a has no simple zeros. All zeros are going to be multiple. Multiplicity greater than or equal to 2. And because for these ramified values, we have the theorem of Nevanlina, which says this thing. Anyway, this is technical, but what is its implication? It implies that a non-constant entire function cannot have more than 2 totally ramified values. And for meromorphic functions, it cannot have more than 4 ramified values. So this thing is to be kept in mind that we are going to utilize this in the proof of this Lappan's theorem. Basically, what we do, we just necessity is all clear because we take this set E to be whole of C, so no problem. Sufficiency is going to be just other way around. Suppose it does not hold. That means the conclusion does not hold. If F is not normal, then we can apply the Zoltzman lemma because it is there in Cn also. By Zoltzman lemma, we can construct this non-constant, non-constant entire function G. And once this function is constructed, then we claim that for large values of J, this Gj, the rescaled sequence, Gj zeta equal to G zeta naught. Whenever zeta J converges to zeta naught, then this thing happens. Once this thing is in place, and remember that this claim is proved by utilizing Hurwitz theorem in one complex variable, and this is the most important trick here because the Hurwitz theorem in several complex variables was not implying us anything. This was the point where we were stuck for a longer time, but somehow we modified the argument and we found out a place for Hurwitz theorem from one complex variable to be applied here, and we got this. And then certainly, so there are certain other conditions, and ultimately what we do, we reach at a point where this G, the entire function G constructed by Zoltzman lemma, it is non-constant there, and we contradict that by our arguments that this G is going to be a constant function, and this contradiction proves your Lappan's theorem in several complex variables, and that Wang's theorem also, that is also proved here as an application of Lappan's, immediate application of Lappan's theorem. So this is what actually I wanted to present before you. This is the latest one, and it is in collaboration with my PhD student Rahul Kumar. And still we are working in this direction. We are trying to find out other applications of Lappan's theorem and other generalization of the results from one variable theory. So I stop here, Professor Sanjeev. Thank you very much.
Thank you, Professor. Yeah, thank you, Professor Charak, for your nice talk. Now the session is open for discussion. Any question or query from the audience? So, Professor Charak, I have one question.
Yeah, sure.
Is there any concept of the quasi-normality of the holomorphic functions of several complex variables?
Yeah, it is not there yet because the work is still in the initial stages, but certainly that concept can be looked at here in several complex variables, because in one complex variable we have that thing.
Yeah.
So the quasi-normality is also one of the questions to be resolved here, but still we are just in the beginning stages. Maybe we can do something in that, or anybody can do, but it is open there.
Yeah. So any other question or query or comment? So as there is no question, let us thank Professor Charak for his nice deliberation. Thank you, Professor Charak.
Thank you. Thank you very much.
Thank you all.
Thank you, sir. On behalf of the organizing committee, I thank you everyone. So have a nice day. Thank you all.
Thank you.
Thank you. Bye-bye.
Thank you, sir.